Good morning, pre-calculus, once again. In this week's live stream, what we want to do is build on what we learned in our last session. In our last session, we looked at how we can use linear functions to model behavior that we observe in the real world, and how do we understand how to interpret the parameters of a linear model. We looked at it first from the point of view of an exact linear model, a line that goes exactly through our data points. But then secondly, and maybe more importantly for practical applications, we also looked at how to obtain an algebraic linear model using linear regression when our data is not perfectly linear, so there's some noise in it, but we can find the line which best fits that data and then do the same interpretive process on that regression model. What we want to do this week is take that same mentality and step it up to make our model more sophisticated. The kinds of function models we want to study in today's live stream are quadratic function models, where linear models can give us graphs that look like straight lines, and so they're really good at predicting behaviors that we observe in the real world that sort of change in a consistent fashion over time, and they always go in one direction. They're either always increasing or they're always decreasing. What quadratic functions give us is a way to model behavior whose directionality might change. For example, we could model, I don't know, the flight of a golf ball that we hit off of a tee, right? The height of that golf ball is going to increase in the beginning, but then at some point gravity is going to take over and it's going to decrease. Similarly, we might model a phenomenon where the opposite kind of thing happens. Maybe it decreases for a while and then starts to increase again. So what we're going to be able to do with quadratic modeling is be able to come up with graphs that are U-shaped, what we call parabolas. And the algebra side of quadratic functions is that we'll be able to do solving and simplifying of equations that now include not just a single power of our independent variable, but the second power of our independent variable. So x squared makes its first appearance as far as the modeling context and the types of functions that we study in today's live stream. So what's our agenda for the day today? What I want us to be able to focus on are the two salient features, the two features that we most are going to care about, particularly from an interpretive context of quadratic functions. Those two features are the intercepts, specifically the x-intercepts of a quadratic function, and the vertex, which is the either maximum or minimum point of that parabola, depending on the properties of the quadratic function, which we'll talk about. So those are the main two kind of questions that we want to be able to ask and answer, and talk about what those things can mean for us in applied sort of real contexts. And we're going to, again, as we did before, start with it from a perfect quadratic function model standpoint, where our parabola goes exactly through all of our data points. Or maybe we start with an algebraic model for a quadratic behavior, and we proceed from the algebra in an exact way. But then before we wrap up today's live stream, I also want to look at how to do the regression process to take perhaps a noisy data set that might otherwise look like a quadratic model and fit a parabola of best fit. Not a line of best fit to the data, but a parabola of best fit. And then be able to, again, engage in the interpretive process of what do the parameters of this quadratic function actually tell me about the real context. So if you're watching today and you're one of my current students, feel free to drop your questions live in our Slack channel, and I'll be happy to respond to those in real time. If you're watching via Twitch, you're not one of my students, feel free to participate via the Twitch chat. I try to respond to any questions that pop up as they arise, prioritizing my current students first. So, quadratic functions. What are we going to care about when it comes to the features that are most important and we're most going to be caring about for quadratic functions? So there are two what I call salient features, two features that are of interest for a quadratic function. For the moment, let's think about this particular quadratic function that has the equation f of x equals 3x squared minus 18x minus 21. So if we were to sketch a graph of this function, y equals f of x, then the shape of this graph would be a parabola. That's something that hopefully is at least passingly familiar to the previous algebra classes that you've had. And so once we sketch a parabola on a graph, there are two key features that we're going to ask about. And the first key feature of parabolas are the places where that parabola intersects the x-axis. So the x-intercepts of the graph, which are alternately called the zeros or sometimes the roots of the function. So when you hear these words, x-intercepts, zeros, roots, all three of those are just different words for the same thing, right? We use the word x-intercepts usually when we're talking about the feature of a graph. We use the word zeros or roots when we're talking about the algebraic properties of the function itself. So how are we going to find those? Well, if we're looking for x-intercepts, as with any graph, we're looking for the places where the value of y is equal to 0. So to find x-intercepts, we're just going to replace the y in y equals f of x, which defines our graph, with a 0, and endeavor to solve the equation f of x is equal to 0. And we know two different ways to solve quadratic equations. We're going to talk a little bit about them both. The first one is, I think, the one that first comes to algebra students' minds because the quadratic formula gets drilled into your head so often in your introductory algebra courses. So if you're comfortable with the quadratic formula, you can, of course, try to use it. It will always work to tell you the roots or the zeros of a quadratic function. All you need to do is supply for this formula the values of the parameters a, which is the leading coefficient, b, which is the coefficient of the first power, and c, which is the constant coefficient. If you plug those numbers into the quadratic formula and turn the crank, as long as you do your order of operations arithmetic correctly, it will spit out for you without fail the x-intercepts of the graph, i.e. the zeros or the roots of our quadratic function. There's one extra feature of there's a couple extra features of the quadratic formula that I want to focus on today because it gives us a lot more information than just the x-intercepts. For example, this quantity underneath the square root of the quadratic formula, b squared minus 4ac, is a quantity called the discriminant. There's your $10 word for today. The discriminant of this quadratic function. And because the discriminant is the quantity that resides under the square root in the quadratic formula, it has the ability, in fact the duty, to tell us how many roots or how many x-intercepts our quadratic equation has. Because if I just draw any old parabola, I can draw parabolas that don't intersect the x-axis at all. I can draw parabolas that intersect the x-axis exactly once. Or, as we've done here, we can draw a parabola that intersects the x-axis in two places. So the discriminant, b squared minus 4ac, is in charge of how many x-intercepts our quadratic function has. So we'll talk a little bit about the discriminant and how that works as well. So the discriminant can answer how many roots. The quadratic formula can answer the question, what are the roots? But the quadratic formula is sometimes too heavy of a hammer for us to use. The more elegant, when it's possible, technique to use is factoring. And so we'll also look at how to place a quadratic function into what's called its factored form. What's great about the factored form, once we factor a quadratic function, is that we can directly read the roots, the x-intercepts of that quadratic function, right off of the factored form. So it's telling us what its roots are. What's really cool about the factored form is it also allows us to do the opposite process. If you tell me what the roots of a quadratic function are, then I can use factored form to build a quadratic function that has the roots that you want. Right? So that's a back and forth kind of process that is maybe a little bit less interesting when we talk about quadratic functions, but in our next chapter, we're going to crank the degree of our polynomials up from 2 to 3 to 4 to 5 and so forth, right? And this same philosophy behind the factored form of a polynomial will continue to serve us well as we look at higher order polynomials. The quadratic formula, by contrast, completely fails. It falls on its face as soon as the degree of our polynomial is larger than 2 in general. In fact, if the degree of our polynomial gets to be higher than 5, then there is not only not an easy formula to use, there's no formula at all to use to find the roots in the general case. So the quadratic formula is something very special to quadratic functions, hence the name. But the factored form approach is something that we'll universalize. We'll be able to use it when we study polynomials of any degree. If we can find a factorization for them, the factored form will tell us the x-intercepts, or the roots. So that's the first important feature that we're going to talk about, our intercepts or zeros. And the factored form is kind of our Rosetta Stone to that. The second key feature is the vertex of the graph, or it's called the maximum or minimum of the function. On my graph here, it's the point where my parabola reaches its lowest point. It's the turning point of the graph is another thing that we could call it. Right? This is the second salient feature that we'll study for quadratic functions. Now, how are we going to find a vertex? How do we find this maximum or minimum point? Very often, the maximum or minimum is the most important feature of a quadratic function, depending on the context of the problem. For example, if I'm a business management marketing major and I'm trying to study, how to price a certain good that I'm trying to sell. I'm trying to slap a price on, my new car or something like that, and I want to slap that price on there so as to maximize, I don't know, maximize the demand for my product, or maximize the revenue, or maximize the profit. That word maximize indicates that what we're looking for here is a maximum or an optimum value for my function. And so we can use the vertex to answer those maximum and minimum questions when we're looking at a quadratic function. In other words, we can use it to optimize, find the situations under which the value of this function is either as large as it can possibly be or as small as it can possibly be. This turns out to be a really important question in calculus, because calculus is going to give us the tools next semester to be able to answer this optimized question in more generality than just for quadratic functions. For quadratic functions, we can study optimum, maximum, minimum questions just using algebra. We don't need the full sophistication of calculus, but calculus will let us answer this question in even more generality than we can in our course. So how do we do it? Again, there's going to be two ways, and the first of those ways is inspired by the quadratic formula. The quadratic formula's discriminant tells us how many x-intercepts it has. But the other piece of the quadratic formula, the minus b over 2a, that piece actually tells us the x-intercept of the vertex. And one of the reasons it can do that, thinking for the moment about the case where, as in our graph here, our parabola has two x-intercepts, two real roots, if you like, then because of the symmetry that a parabola has, every parabola is symmetric about its vertical axis of symmetry. Because of that symmetry, the vertex is always going to be exactly halfway in between the two x-intercepts, when those two x-intercepts are real numbers. Right? And so that's why minus b over 2a tells me the x-coordinate of the vertex, because the x-intercepts are found by adding and subtracting the same quantity, square root of b squared minus 4ac, to that x value. So minus b over 2a can directly tell me the x value of the vertex of a parabola. Then that's really slick. It's really clever. And if all we care about is the maximum or minimum value of a quadratic function, that's a really quick and dirty way to get started. But because we also just finished in Chapter 1 talking about graph transformations, there's also an elegant form in which we can express a quadratic functions formula called the vertex form. And in the vertex form, what we've done is we really realized this graph as a transformed, so a stretched and flipped and shifted version of the graph of y equals x squared, the basic shape of a parabola. But once we've realized it using those stretches and shifts, it's exactly these shifts, the horizontal shift that we see right here and the vertical shift that we see out here, those shifts determine for us the x-coordinate and the y-coordinate of the vertex of my parabola, this h and that k. And the reason that that works is that our basic shape, y equals x squared, has its vertex at 0, 0 at the origin. So when I subtract h from x, that vertex moves to the right by h units. And when I add k, in this case k would be negative because I'm moving this down. When I add k, I'm moving that vertex down to have a y-coordinate of k. So this is the basic outline for what we're going to talk about. How do we find intercepts or zeros, and how does the factored form play into that discussion? And then how do we find the vertex, the maximum or minimum of a quadratic function, and how do we discover the vertex form as a part of that process? So let's stick with this same function and move forward to actually look at how to do these processes and how to think about these processes, perhaps more importantly. So f of x equals 3x squared minus 18x minus 21. First question I want to ask are about the intercepts. And I actually am going to ask this question not just about the x-intercepts of this function, but also, since we're on the topic, let's also talk about the y-intercept of this as well. So how do we do it? Nudge this down a little bit, sorry. So for the y-intercept of any graph, remember anytime we talk about intercept, what we're talking about is where does the graph intersect one or the other of the coordinate axes. And for the y-intercept, we want to know, where does my graph cross the y-axis? Well, my graph, any graph, is going to cross the y-axis where the value of x is equal to 0. Right? So all the coordinates of points on the y-axis have their x-coordinate of 0. 0, 0, 0, 1, 0, 2, and so forth. So to find the y-intercept of this graph, I just need to ask what happens when x is equal to 0. So I'll just put in a 0 for my x. I'll evaluate this function for the x value, 0. F of 0 is equal to 3 times 0 squared minus 18 times 0 minus 21. Stick that 0 in there. Don't forget my square on top here. But something that you'll notice when we do this evaluation is that anytime x is equal to 0, any power of x is also equal to 0, and any multiple of x is also going to be equal to 0. So this term, 3 times 0 squared, is just going to be 0. 18 times 0 is likewise going to be just 0. And so the only thing that survives in my evaluation is that constant at the end, negative 21. So if the question is, what is the y-intercept of this graph, then I know my x-coordinate of the y-intercept is going to be 0, and my y-coordinate is going to be negative 21. So there's my y-intercept, 0, negative 21. I'll place that point on my graph over here. Notice my graph has blank scale on my axes here, so I can decide my scale is whatever I want to. I'm going to pretend that my y's are counting by 5s. So just for the sake of completeness, let me mark on here. This is negative 5, negative 10, negative 15, and so forth. And counting upwards, we'll have 5, 10, 15. So there's the scale on my y-axis. And now, according to the work that we just did, the y-intercept is right about here at 0, negative 21. Great. So now that we've found the y-intercept, we have one point on the graph of my parabola. And as we discover more about this quadratic function, we're going to be able to place more of the salient features of this function as part of the graph. And it's that interchange between graph and algebra that is really at the heart of pre-calculus. We want to understand our functions that we study from all those viewpoints: algebraic, graphical, numerical, and also verbal and interpretive. So that interchange is super important for us. Now that we have the y-intercept placed, it's a much more interesting question about the x-intercepts. How do I figure out where the x-intercepts are? Well, again, if we're looking for the x-intercept, all the coordinates of the points on the x-axis have y equal to 0. Right? That's what all the points on the x-axis have in common. So we just turn the logic from x-intercepts on its head and say we want to look for what happens when y is equal to 0. And so what that's going to require us to do is it's going to require us to solve an equation. Let me make some space up here above my graph to do this part. So what our job is our job is to solve f of x is equal to 0. And f of x here, 3x squared minus 18x minus 21, is a quadratic function. Which means, if I'm going to solve this equation, I have really two strategies that we talk about. The first one is just to use the quadratic formula. So if I were to use the quadratic formula, let me find a place to write my quadratic formula here. I'll write it down just next to my head. So my quadratic formula says the value of x should be equal, whoops, leaning the wrong way, to minus b plus or minus the square root of b squared minus 4ac, and that whole thing gets divided by 2a. Right? So if you have this formula written down on a reference card somewhere, or you look it up online, or maybe you committed it to memory with some clever jingle that some algebra professor taught you at some point, if you remember this quadratic formula, and if you're studious with the order of operations, it will always work. So let's do our due diligence here and plug in our values for the coefficients a, the leading coefficient, b, the linear coefficient, and c, the constant coefficient. So I'm just going to pluck those out of my formula. And by the way, before we can even use this formula, we need there to be a 0 on the right-hand side of this equation. That's just a reminder. The same is going to be true for all of our factored form considerations as well. We want to get all of the variables and constants to one side of our equation and a 0 on the other, because otherwise we don't have any way of using these strategies. So I'll plug in here, in place of my a's, I'll plug in a 3. So I'm going to take the liberty of just erasing here. Plug in a 3 there. Plug in a 3 here. Whoops, I'm starting to screw up my formula. I'll plug in a negative 21 for c right there. Times 3 times negative 21. Make sure that my square root goes far enough and my fraction bar goes far enough. And then for my b, I'll plug in negative 18. Notice I'm trying to be really careful with parentheses, because the best way to screw up your evaluation of the quadratic formula is to lose a negative sign somewhere. So try to avoid it. Negative 18 goes here, parentheses negative 18 goes there. Okay, so I've plugged in all of my values. I've evaluated my quadratic formula expression for a equals 3, b equals negative 18, and c equals 21. So now all that's left to do is to evaluate. And the first thing that we would evaluate in this quadratic formula is we would go underneath the square root sign and evaluate what's there. Because the square root sign acts like a grouping symbol. It acts like parentheses. And so in the PEMDAS hierarchy, it's the first thing that we would do. So I'll go underneath that radical. Negative 18 squared, that's negative 18 times negative 18, and my brain is not working at 100% with arithmetic this morning, so I'm going to do that just with a calculator. 18 times 18, there we go, 324. And so underneath my square root, I'm just going to put that piece over here. I'm going to get 324. And then I've got 4 times 3 times negative 21. So 3 times negative 21 is negative 63. Negative 63 times 4, that's 252. And that gives me a negative sign. So negative 252 is what I get when I do 4 times 3 times negative 21. But then there's a minus indicating I need to subtract these two. See what I mean about how the best way to screw up the quadratic formula is to screw up your signs? That, I think, is the source of at least 75% of people's mistakes using the quadratic formula, is just getting a sign out of place. Because now that I see what's underneath the radical, 324 minus negative 252, minus the minus turns into a plus. And 324 plus 252, again, pulling out my calculator, that's 576. And here is where I'm going to pause. I want to stop this evaluation right now, because I want to make an observation. And I want to give us some tools to make similar observations with other kinds of parabolas, other kinds of quadratic functions as well. We've just figured out that the square root in my quadratic formula is going to have the number 576 under it. Now, what's important about that number? That number is going to be able to tell me how many x-intercepts that we have. That number, 576, is called the discriminant of this quadratic. Discriminant. And we got it by evaluating b squared minus 4ac. b squared minus 4ac is 576. Right. Now, without actually doing the arithmetic, let's game out what's going to happen next in my quadratic formula. We're going to take that 576 and we're going to take its square root. And that square root is going to give me a number. And that number is going to be a real number because 576 is positive. Then I'm going to add and I'm going to subtract that positive number from 18, and I'm going to divide the result by 6. But when I add and subtract this positive number, positive real number, from 18, I'm going to get two different values, 18 plus something and 18 minus something. Those values are different because this something is a positive real number. And therefore, the quadratic formula is going to give me two x values. And therefore, we're going to have two x-intercepts. We have two x-intercepts precisely because this square root gives me a positive real number. It's a real number because 576 is non-negative, and it's a positive number because, furthermore, 576 is positive. So there is our sort of classification for how we can use the discriminant. When the discriminant is positive, that means that there is two x-intercepts, two roots, if you like, for my quadratic. When the discriminant is negative, let's game that out for a second. What would happen if my discriminant were negative? For example, what would happen if there were a minus sign in front of my 576 right here? Well, what's the square root of a negative number? Negative numbers have square roots, but those square roots are not real numbers. The square roots of negative numbers are imaginary, or complex, if you like. We don't really study imaginary numbers in this particular pre-calculus course, but they have actually, believe it or not, a wide variety of uses. Despite the name suggesting that they're a figment of our imagination, imaginary numbers are actually very real. They're just not real numbers. Anyway, because the square root of negative 576 is not real, that means that the solutions of this quadratic equation up here are not real. And therefore, there are no places on the real x-axis where this graph crosses. So there are no x-intercepts in the case where the discriminant is negative. When the discriminant is negative, our quadratic function has no roots at all. And then there's the case in between, when the discriminant is equal to 0. Imagine for a moment that the discriminant of this quadratic were equal to 0. Well, what's the square root of 0? That's a real number. The square root of 0 is just 0. But when I take that 0 and I add and subtract it to 18, I no longer get two different values. I only get one. Namely, I get 18 up in the numerator. And so if the discriminant happened to be 0, that means that there would only be one place where this graph crosses the x-axis. There would only be one root for my quadratic. So there's the full sort of classification. And just for fun, let's take a step out and look at some different cases, right? Just to kind of verify this behavior that we think that we're seeing, right? So here's a little nifty Desmos app in which what we're going to be able to do here is, let me actually make some space so you can see this above my head. What we're going to do with this is change the values of a, b, and c, and observe what happens to the value of the discriminant. So this little box above my head here is recording the discriminant of this quadratic as I change the values of a, b, and c. For example, this quadratic has a equals 3, b equals 1, c equals 2. So this is 3x squared plus 1x plus 2. Right? And this parabola does not cross the x-axis in any point. And the discriminant is telling me that because the discriminant is negative 23. Whoops, you can't see it. I just realized that I didn't hit the transition button. There we go. Now we can see what I'm pointing at. Sorry about that. So this is the quadratic 3x squared plus 1x plus 2. F of x equals 3x squared plus x plus 2. And because this parabola does not cross the x-axis in any place, right? It has no x-intercepts at all. And that's reflected in the fact that the discriminant, negative 23, is a negative number. But if I start changing the values of these parameters, so if I vary the value of a, my discriminant is still negative, and we can tell because the graph still does not cross the x-axis. But at some point, if I keep changing my a, eventually, now look what's happened. If I change my value of a, now it's negative 3. So this is y equals negative 3x squared plus x plus 2. Right? Now my discriminant, 25, is positive. And now that my discriminant is positive, my graph crosses the x-axis in two places. Once right there, and once right there. Right. And if I change my other parameters, we can also sort of see what's happening with the discriminant. The discriminant here is still positive, and I still have two x-intercepts. But eventually, if I change this enough, the positive becomes, oh, so here's an interesting example. Now my discriminant is equal to 0. And take a look at what's happening with my parabola. My parabola is only touching the graph, touching the x-axis just once. So this parabola has only one x-intercept. This quadratic function, which happens to be f of x equals negative 3x minus 6, negative 3x squared minus 6x minus 3, has only one root, only one place that it's equal to 0. But if I keep going, I can make it again so that my parabola does not touch the x-axis at all, and my quadratic has no roots, and now my discriminant is negative again. So the discriminant tells us the full story about how many times a parabola crosses the x-axis, or how many different values of x make our quadratic function equal to 0. When that number is positive, when the discriminant is positive, we have two x-intercepts, in other words, two roots. When that number is negative, oops, I can't make it negative by changing b. When that number is negative, here we go. When that number becomes negative, we now have no x-intercepts. And when that number is 0, which is touchy, I have to try and slide this around a little bit to make it happen again. No, still not working. Gotta try to make it 0. How do I do it? Uh-oh. All right, well, you can rewind the video if you like. I'm having some trouble finding a good example where it's 0 again. But when that discriminant is 0, we have exactly one x-intercept. In other words, one root that we can get, one place where my parabola crosses the x-axis. Okay, so coming back to the work that we're doing here. Now that we know that the discriminant tells me the number of x-intercepts, and in our case, because my discriminant was positive, we know that we're in this case. We know that this parabola is going to have two x-intercepts. This quadratic function is going to have two roots. And so we can find them, again, by finishing my quadratic formula evaluation. Take 576, evaluate its square root, So I'm just going to hit my square root button up here. Boop. The square root of 576 happens to be 24. So this particular example is one where that square root turns out to be a pretty nice number. It's an integer. It's a positive integer, right? And that's nice because now we know that my roots are going to be rational numbers. 18 plus 24, that's going to be 42. 42 divided by 6 is going to give me 7. And on the other hand, 18 minus 24 is negative 6. Negative 6 divided by 6 is negative 1. So we've now completed our quadratic formula evaluation, right? We now know that the intercepts of this parabola are going to have x coordinates of respectively 7 and negative 1. So let's put those, first of all, into their ordered pairs, negative 1, 0, and 7, 0. Those are going to be my x-intercepts. And now we'll just place those points onto our graph. I'm going to remind myself here of what scale I'm using on my axes. Let's use 1s when we count the x direction, 1, 2, 3, 4, and so forth. And so if I do that, that means that x equals negative 1 is going to be right here. So that's the point negative 1, 0. And x equals 7 is going to be right there. That's going to be the point 7, 0. So we're in pretty good shape right now. We've got the y-intercept of my graph already plotted. I've got both of the x-intercepts of my graph plotted. But before we go on to finish the graph, and the way we're going to finish the graph is by finding its vertex, before we go there, I want to take this opportunity to talk about finding the x-intercepts using factoring rather than using the quadratic formula. Because the quadratic formula, because it works all the time and it's so flexible, it also is not very elegant, right? We often have to do a lot of arithmetic to succeed in the quadratic formula evaluation, and it's really a fraught with danger evaluation because there's so many negative signs and the square roots and all this order of operation stuff. So if you can factor, I recommend you factor. Always, every time. So let's look at what the factored approach is going to allow us to do here. How do we find the factored form of a quadratic? And then what do we do with that factored form to figure out what it tells us about the intercepts and the features of our graph? So as the name suggests, probably the first thing that we would want to do if we're trying to use the factored form or to learn something about my quadratic function through a process of factoring is I should try factoring I should try factoring my left-hand side of this quadratic equation. If we're trying to find the x-intercepts, that means we're still trying to solve this equation. 3x squared minus 18x minus 21 is equal to 0. So as long as we're still trying to solve that equation, any strategy that we could use to solve a quadratic equation is still on the table. And besides the quadratic formula, the other strategy is to use factoring. So let's get a quick refresher on how to use factoring to solve quadratic equations. I'm going to dip into one of my videos real quick. Let's watch it together. And then afterwards, we'll come back and apply it to this particular problem. So here is my solving a quadratic equation using factoring video. Let me cue it up for you here. And let's take a gander. That 0 on the right-hand side is fundamental to this technique. If you don't have it, you can't move forward yet. But as soon as one side of our equation is equal to 0, now we can use factoring on the other side. Our left-hand side, x squared minus 5x plus 6, is a polynomial expression whose highest exponent is 2 and which has 3 terms that are not like to one another. That makes it a quadratic trinomial. And since its leading coefficient, the coefficient in front of x squared, is 1, we can use the sum and product method that we saw in the previous video to try to factor it. That method will require us to find a pair of integers, if they exist, which multiply together to give us 6, and which add together to give us negative 5. So starting by thinking of numbers which multiply together to give me 6, I might think about positive 6 and positive 1, positive 3 and positive 2, but then also negative 3 and negative 2, since negative times negative is going to give us a positive, and negative 6 and negative 1. Of those possibilities, the one which also adds together to give us negative 5 is the pair negative 3 and negative 2. Using the sum and product factoring technique, we may therefore factor the left-hand side of this equation into the product of binomials x minus 3 times x minus 2.
At this stage, having accomplished the task of factoring, sometimes students forget what they're doing midstream and forget that there's an equation still involved. We still have an equal sign, and we still have a right-hand side, which is 0. So we're not done yet. We still have to discover what value x should have. Discovering the value for x uses a strategy that factoring makes possible by using a property that exists in the system of real numbers. The property is called the zero factor property, and it states that it is impossible to multiply two numbers together and get an answer of 0 unless one or both of those original numbers was itself equal to 0. The number 0 is unique in this property in the real number system. We cannot multiply together to get a product of 0 unless one of our original factors was already 0. We can leverage that fact by taking our equation, which is now a factored expression on the left-hand side and a 0 on the right-hand side, and splitting that single complicated equation into two separate, simpler equations by giving each one of the factors its own equal to 0.
So I want to pause the video right here just to underline this fact because, again, as I mentioned in the video here, this is the most important thing to know about factoring, is that the whole purpose is that it allows you to take a complicated equation, and once it's been factored and there's a 0 on the right-hand side, to split those factors apart so that each one of them can be a simpler equation set equal to 0. Just wanted to cut in here and underline that fact, even though I already underlined it in the video itself. That is the reason why we care about factoring, is that it allows us to split equations that are complicated into a set of equations that are simpler and then solve them. So don't forget that zero factor property. Let's pick up where we left off.
This step has replaced one challenging equation with two much less challenging equations. And the path forward is then just to solve each one of those simpler equations to discover values for x. I can solve x minus 3 is equal to 0 by adding 3 to both sides. I get a solution, x is equal to 3. And I can solve x minus 2 equals 0 by adding 2 to both sides and getting the solution x equals 2. So at the end of this process, we now have values. We actually have two different values that the variable x can take that will balance, make both sides of the original equation the same. X equals 3 and x equals 2. And so we will list both of those as our solutions, x equals 2 and x equals 3. So to use a factoring technique to solve a quadratic equation, the most important first step, and we can't do any factoring until we're done with this step, is to use subtraction to make one side of that equation equal to 0. Until you have a 0 on one side, you cannot go forward. But once you have a 0 on one side, then you can start to think about factoring the other side. In this example, we had on the other side a quadratic trinomial whose leading coefficient was 1, which meant that we could use the sum and product method, as you see up here, to factor it into the product of binomials x minus 3 times x minus 2. And that's when the real magic happens at the next step. Because when a product of two things is equal to 0 in the real number system, it means that either the first factor was itself equal to 0 or the second factor was itself equal to 0. In other words, we can split this one challenging equation into two simpler equations and solve each of those simpler equations individually to discover our answer. Notice also, something happened in this equation that hasn't happened in the other equations we've solved in this course so far. This equation had two different solutions that we need to report both of. That didn't happen when we were solving linear equations.
All right, so that's the lowdown on just refreshing your memory on how factoring can help us to solve quadratic equations. It's an alternative and a more elegant alternative to the quadratic formula. Of course, the downside is that because it's more elegant, it also doesn't always work. Not every quadratic equation can be factored in this way over the rational numbers, because it's not always possible to solve this sum and product game that I talked about.
But it can happen,
right? There's not always a pair of numbers that multiplies to exactly the right thing and adds to exactly the right thing. But when there is, factoring is the way to go. It really is the most elegant way forward. So let's apply that mentality here to this example. If I want to solve this equation, 3x squared minus 18x minus 21 is equal to 0, then because I have a 0 on this right-hand side, factoring seems like a good option if we can do it. So we'll put our factoring hats on and ask, first of all, is there any common factor that's common to all three of those terms that we can at least get the process started by bringing out? That answer is yes. All three of my terms here are divisible by 3. So I'll bring a 3 out. I still have equals 0 on the right-hand side. And then when I pull out that 3, the cofactor that goes with it is x squared minus 6x minus 7. Right? So now I factored out the greatest common factor, which means that there's no common factor left for all three of those terms. So my next step should be to try to factor this quadratic trinomial. Playing the sum and product game again, we want a pair of numbers, rational numbers if they exist, that when I add them together I get negative 6, and when I multiply them together I get negative 7. And I find out that the pair of numbers that does that fits that bill, is negative 7 and positive 1. Negative 7 times positive 1 is negative 7. Negative 7 plus positive 1 is negative 6. And so I have factored this quadratic completely at this point. So what's great about this is a couple things. So now that we've factored this, f of x is equal to 3 times x minus 7 times x plus 1. And we already found what the x-intercepts, or the roots of this polynomial, were previously using the quadratic formula. But what I want to do for us right now is I want to draw the connection here between the factored form of this quadratic and the knowledge that we have now of the x-intercepts that we got from using the quadratic formula. So what do we learn? First of all, the roots of this polynomial, this quadratic, were negative 1 and positive 7. When I look at the factored form of this parabola, I see the number 7 sitting right here in this factor, and I see the number 1, it looks like a positive 1, sitting right here, but negative 1 happens to be the root. So the first thing that I would say that we can notice here is that somehow the opposites of these numbers, the opposite of this positive 1 is negative 1, and that's one of my roots. And the opposite of this negative 7 is positive 7, and that's the other one of my roots. Those opposites seem to give me the roots. Opposite of the roots. Now, why should they be the opposites? Well, there's a really good reason for that. Because if I replace my f of x here with a 0 to try and find the roots of my polynomial, what am I going to do? I'm going to use the zero factor property to break apart these factors and give each one of them their own 0. And so I'll get one equation that says x minus 7 is equal to 0, and I'll get another that says x plus 1 is equal to 0. And when I try to get those x's by themselves, I have to respectively add 7 to both sides, which will have the result of adding 7 to 0, and also subtract 1 from both sides, which has the effect of subtracting 1 from 0. Plus 7 minus 1, so x is equal to 7, and x is equal to negative 1. So it's this last step here that explains why the numbers that we see here are the opposites of the roots of my quadratic. And so when I have a quadratic function placed into its factored form, the opposites of the numbers that are added to the x's here, the opposites of those are the roots. Or another way to say that is to say that in the factored form of a quadratic, the factors are x minus a root times x minus a root, right? So the minus here is taking care of our opposite thinking, right? So x minus blank. Having a factor of x minus something as part of the factored form of my quadratic tells me that that something, that number, is one of the roots of that quadratic. So factoring is a very powerful tool for us to discover the roots. And also, it lets us do the opposite process. If you were to tell me what the roots are that you want for a quadratic, I can produce a quadratic that has those roots. Just as an example, let's suppose that I know, if I know that f of x is quadratic, and its roots are, let me pick a couple of roots. Let's say x equals negative 1/3 and x equals 9, or something like that. Then the factored form lets me find an equation for the quadratic that has these properties. All I have to do is create a pair of factors, and the beginning of those factors is x minus, and the end of those factors is the roots that I want. So x minus negative 1/3 and x minus 9. And there I have an example of a quadratic function that's going to have these two roots. Now, we could also put a number called the leading coefficient out here in the front if we wanted to. That's not going to change the roots. It is going to change the other features of the parabola. It's a vertical stretch or a vertical shrink, right? So it's going to change how wide or how narrow the parabola is, but it's not going to change where that parabola intersects the x-axis, because that's determined by these two factors. If I wanted to, I could also multiply this out to find the standard form. I would get x squared. Let's turn this minus and minus here into a plus, just to save ourselves a little cognitive load there. I'm going to get negative 9 plus 1/3. That's going to be negative 26/3 times x. And then negative 9 times 1/3 is negative 3. Right? So there's an example of a quadratic function that has these two properties. It has those two roots. But again, as I mentioned before, we can stick a leading coefficient out here in the front, and it will still satisfy these two things. For example, if I stuck negative 6 out of the front here, just picking that number at random, right? Then when I simplified this out, I would get a different standard form. Negative 6 times x squared minus 6x squared, and then I'm going to get minus 52x plus 18. And so that's another example of a quadratic function that has these two roots. It just now has a different vertical, actually in this case it's been vertically flipped, and it's also been stretched out by a factor of 6 compared to our first example here. But it still has those two roots. So if you tell me the roots of a parabola, or of a quadratic function, I can tell you a formula for that quadratic just by using this factored form. And for me, that's really one of the coolest parts about the factored form, is that it lets us do that. So that's the lowdown on the intercepts, finding the intercepts of a quadratic. So where do we need to go next? Just give me a minute here to reset my scene. So the next thing that we want to be able to do is we want to be able to discuss the vertex. Sorry, I gotta erase my whiteboard here a little bit, but I want to keep the features of the graph that we worked so hard to find. Okay, so let's go back to where we were. Get everything set up here. Okay. So now that we understand how to find the intercepts of a parabola, and we did it in two ways. We talked about the quadratic formula, but we also talked about the factored form of our parabola. And since we've got a fresh start here on the screen again, let me put that factored form back, just so that we continually remind ourselves. 3 times x minus 7 times x plus 1, or another way to say it is minus negative 1. Right? And it's these numbers, 7 and negative 1, that were our x-intercepts, or the roots of our quadratic. Now, how do we find the vertex? How do I know what is the lowest point or the highest point of the graph of this parabola? And there are two different ways to find a vertex. There's probably more. I mean, when you go to calculus, there's a third one that we won't talk about today. But we can find the vertex, first of all, inspired by the quadratic formula. So, using the quadratic formula to find a vertex, let's put the quadratic formula back on the screen here. The quadratic formula does not find the vertex for us directly, right? It finds for us the x-intercepts, right? That's the purpose in life of the quadratic formula, is it tells us where a quadratic expression is equal to 0. But what's great about it, remember we talked a few minutes ago about how the discriminant tells us how many roots that there are, how many x-intercepts for our parabola. And it tells us that because it's what we're adding and subtracting to minus b in my quadratic formula. Or another way to think of it is we're adding or subtracting it to minus b over 2a. So what I'm going to do actually to start our thought process is I'm going to split this fraction in the quadratic formula into two pieces. I'm going to split it into minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. So this is another way to understand the quadratic formula. Right? But when I do this, the square root of b squared minus 4ac over 2a is what I'm adding or subtracting to this x value to find the x-coordinates of my intercepts. So what that tells me is that this x value is exactly halfway in between my two intercepts. Now, what do we take from that observation? What we can take from that observation is that there is a vertical line at a certain value of x. I'm going to sketch it in here on our graph real quick. There's a vertical line that I can draw at a certain value of x, and that the two x-intercepts of my graph are equidistant from that vertical line. So in this example, when we use the values of a, b, and c that we get out of this quadratic function, we ended up with minus b, that's 18, over 2a, that's 6, plus or minus the square root of b squared minus 4ac, that was 24, divided by 2a, which was 6. Right? And so we do this whole evaluation. We simplify what's there, and 18 over 6 becomes 3. 24 over 6 becomes 4. Right? So where do I find that 3 and that 4 on my graph? Well, first thing we notice is that this 3 is going to serve as our center point. This is the value of x that defines for me this vertical axis of symmetry of my parabola. The axis of symmetry is a vertical line, and the vertical line has the equation x equals 3. Okay? And that's where this 3 is coming from. Right? It's the center point equidistant to which I can find both of my x-intercepts. Then, this number 4 that I see sitting out in front here, the thing that I'm plus and minusing to my 3, that tells me how far away from my axis of symmetry I will find my two intercepts. Plus 4 on the one side, minus 4 on the other side. Right? If I add 4 to 3, I get 7. If I subtract 4 from 3, I get negative 1. Right? And so just by slowing down our cognition about the quadratic formula, we found out that it tells us more than just the intercepts. It tells us the axis of symmetry. How does it tell me the axis of symmetry? It tells me the axis of symmetry by evaluating this quantity, minus b over 2a. Right? Minus b over 2a tells me the x value of my axis of symmetry. And, more importantly to our current question, the axis of symmetry will also contain the vertex. The vertex of a parabola always lies on the axis of symmetry. Right? So this tells me that my axis of symmetry is x equals 3, and therefore the x-coordinate of my vertex is x equals 3. And that is a big win for us. Because as soon as I have the x value, I've done the hard part. Right? If I'm trying to find the coordinates of any point on the graph of a function, knowing the x-coordinate is sufficient. Because as soon as I know the x-coordinate, I can find the y-coordinate because y is equal to f of x. So I'll just evaluate that y-coordinate by evaluating f of 3. And so that's going to be 3 times 3 squared minus 18 times 3 minus 21. Stick my 3 in there. 3 squared is 9 times 3 is 27. 18 times 3, unless I miss my guess, is 54. And then I'm going to subtract 21. I finish all that arithmetic. I get negative 48. I think that's right. I hope that's right. And if that's the case, then that becomes the y-coordinate of my vertex. 3 comma negative 48. And so on my graph paper, here I'm counting by 5s. I'll go down 5, 10, 15, 20, 25, 30, 35, 40, 45, and then in between 45 and 50, so right about there, is where I will find my vertex point. 3, comma, negative 48. And there's my vertex. Right? So this is the quick and dirty way. I feel like this is probably the way that most students, if you're looking to save mental energy, this is the way that you're going to use to find the vertex for a parabola, if that vertex is unknown. Right? And now that we have the x and y intercepts and the vertex and the axis of symmetry, I think now is a good time for us to just go ahead and sketch the graph of this parabola. Let's just get it down on the page so that we can be done with this graphing portion. Because the vertex, again, is going to be the lowest point on my parabola. So that x-intercept is going to connect to it. It's going to connect on this side to the y-intercept and then to the other x-intercept. And then I'm just going to kind of continue my line, continue my curve here as best I can. So now there is a graph that contains all of the salient features of this quadratic function. Right? We know the vertex, we know the intercepts, and that was really enough. And we know the axis of symmetry. But before we move on to talking about the vertex form in a different way, I also want us to think about how we could have known whether or not this vertex is a max or a min point. Does this vertex represent the highest point on a parabola, or does it represent the lowest point on a parabola? Now that I have my graph, it's kind of obvious, right, that this vertex ends up being a minimum value, not a maximum value. But what is it about the formula that could have told me that? I want to go back to our Desmos Explorer here for just a moment. And we're going to talk about what it is. Sorry, let me get us transitioned back over. Here we go. Okay. So how could we have known whether or not a parabola's vertex is indeed a maximum or whether it's a minimum point? How I like to think of it is think about the basic shape of a parabola, y equals x squared. Y equals x squared is a parabola that opens upward, as this one over here does, right? This is y equals x squared. And what is it about the parabola that is going to change which direction that it points? If I change the constant coefficient, the c, it's not changing whether this parabola is pointing up or pointing down. It's only applying a vertical shift to my parabola, right? Which should be expected. Adding a constant to a function always has that effect on its graph. It just shifts it up or it shifts it down. Similarly, changing the linear term, the coefficient attached to the x, does not look like it's changing at all whether or not this parabola opens upward or opens downward, whether its vertex is a maximum or whether its vertex is a minimum. Changing this value of b, no matter where we put it, always preserves the fact that the vertex is still a minimum, just like y equals x squared was. So it must be the a coefficient. After all, the a coefficient looks like it's applying a vertical or a horizontal stretch and shrink to this parabola when a is positive. But when a becomes negative, that so far is the only way that we've been able to change whether the vertex is a maximum. Now my vertex is a maximum value, it's the top of the hill, versus a minimum, the bottom of a valley, as it is when a is positive. So what we can take away from that is that whether or not the vertex of a parabola is a maximum or a minimum depends completely on whether or not the leading coefficient, the value of a, is positive or negative. Our vertex will be a maximum when a is negative, and will be a minimum when a is positive. And in our example that we're working with right here, our value of a is positive 3, right? The leading coefficient, the coefficient of x squared. So since our value of a is positive 3, that means that our vertex is a minimum. A quick note here to say that this intuition is a little bit counter, right? When our brains hear the word maximum, we like to think of big things, and so we like to think of positive numbers, and in fact, it's just the opposite, right? That our vertex is a maximum when a is negative and a minimum when a is positive. Next semester in calculus, there's a test for any optimum point of any kind of function, not just quadratics, that can tell us whether that critical point, that turning point, is a maximum or minimum. And it's also counterintuitive like this. There's a quantity called the second derivative. And when the second derivative is positive, we're at a minimum. When the second derivative is negative, we're at a maximum. So this same counterintuition, straighten it out for yourself here in pre-calc, and then you'll save yourself some time later in calculus when you have to do the same thing for functions that are no longer just quadratic. So this is the quadratic formula approach to how to discover the vertex for a parabola. But I don't want to leave well enough alone, because I never do, right? And so I want to talk about how we can use algebra to discover the vertex in a different way by discovering what's called the vertex form of a quadratic function. So how does the vertex form work? Well, I want to actually go back to our Desmos graph yet again. So here is our original y equals x squared graph. This is our prototype parabola, right? Its vertex is at the origin and it opens upward. Now I want to think about what it would take for us to turn this graph into that graph. And we are already equipped this semester in pre-calculus to know how to do that. Because this graph is the graph of a parabola, and because this graph is the graph of a parabola, all parabolas are similar to one another. We can turn our original parabola into the one that we want by doing nothing more than flipping, stretching or shrinking, and shifting. In other words, applying the graph transformations that we learned about in our first topic of the semester, back in topic A. So what graph transformations are going to be needed in order to make this thing work the way that I want it to work? Well, the first thing that I likely want to do is, let me actually get a new graph window here. Save this one and just get a blank one. F of x equals x squared. So the first thing that I'm going to want to do, let me actually try and look at these two things side by side just so we don't lose the tune here. There we go. I want to make it a little bit more readable quick. Projector mode. All right, we can kind of see it. So if I want to turn this y equals x squared graph into the graph of the function that we care about right now, then the first thing, remember, the first thing that we always do when we're thinking about transformations, if there's multiple of them to do, always think about stretching, shrinking, and flipping, multiplication. Think about those first, and think about shifting last. So what shrinking, stretching, or flipping am I going to want to do to this parabola? Well, to this parabola, let me actually set up my axes here so that the axes are the same also. So I'm going to set my y-axis to go minus 40 to 40 by steps of 5. And okay, so now our coordinate axes look relatively similar. So what it looks like I want to do is it looks like I want to shrink this parabola. I want to either shrink it horizontally or equivalently stretch it out vertically. I'm going to take the latter viewpoint. I want to stretch this thing out vertically. And the amount that I want to stretch it out vertically is actually shown to me right here in my leading coefficient. I should stretch it out by a factor of 3. So if I do that, then let's make our original graph this dotted line right here, dashed line. In order to stretch it out by a factor of 3, what I ought to do is multiply f of x by 3. If I do that, now my graph has the requisite narrowness, right? Now my parabola looks like it has the right width to match up with the answer that I'm looking for here. So I've done my vertical stretch by a factor of 3. Let me just make a note that that's what we just did. Vertical stretch by a factor of 3. Great. So now we have the width that we wanted. What happens next? Now we need to shift. Now that I'm done doing all of my stretching, I didn't need to flip because my parabola that I am looking for opens up and my original parabola also opened up. So now I'm ready to start doing my shifts. And my vertex tells me how much I need to shift by. Right? Because my original vertex is at the origin, 0, 0. My vertex that I want is at 3, negative 48. And so the steps I want to do is I want to shift, I want to shift to the right by 3 units. And I also want to shift down by 48 units. 48. And once I do both of those things, then I should have exactly the equation that I'm looking for. So let's do it. How do I shift this to the right by 3 units? I want to replace x by x minus 3. So instead of 3x squared, I have x minus 3 times the quantity x minus 3 squared. Right. And so now my new parabola, oops, I'm going to change the color here just so that we don't get confused. My new parabola has been moved over by 3 units, which is what we wanted, because after all, my axis of symmetry for the parabola I want is x equals 3, not x equals 0, the y-axis. And now to finish, I just need to shift that down by 48 units. And to shift it down by 48 units, sorry, let me change the color one more time, just so that we're not getting confused here. To shift this parabola down by 48 units, I'll take the equation that we had here, 3 times quantity x minus 3 squared, and I'll just subtract 48 from it. Whoops, let me zoom out just a little bit. Change my y-axis coordinates, minus 60 to 60. There we go. And I'll change the color to match up with the color I have on the screen. Now we're done. Now we've done all of our transformations in order to get my parabola to be exactly the one that we wanted. Its vertex is at 3, negative 48, and it opens upward and it has the right requisite narrowness. So at the end of this process, take a look at what we've just won for ourselves. We've just won a new equation to describe f of x. So let me record that equation. You're not going to be able to see me writing here for just a moment, so don't worry about that. You'll see it in a minute. But my new equation looks different to the one that we just started with. I'll draw it underneath here. Sorry. So f of x is equal to 3 times the quantity x minus 3 squared minus 48. That equation now is an equation for my quadratic function. That is telling me the vertex. How is it telling me the vertex? Well, in a similar fashion to how the factored form told us the x-intercepts, the vertex form, so that's what we call this form of the equation, vertex form. Vertex form tells me the vertex by showing me right here the x-coordinate of my vertex. This 3 is exactly the x-coordinate that we had in my vertex. 3. And the constant which is being added out here in the front, negative 48, that's telling me the y-coordinate of my vertex. So the vertex form is the right form in which to directly read off the vertex of a parabola, where the factored form was the right way to write down a quadratic function so as to read off its x-intercepts. So you might ask yourself, if I don't have a nifty, handy-dandy Desmos graph transformation calculator to do this work, how could we do this work using algebra? How do we discover the vertex form of a parabola by using algebra rather than using technology? And this is a technique of algebra called completing the square. Completing the square is an algebraic process that you may have gotten some exposure to in your algebra classes, and you may not have. So I'm going to borrow a video from YouTube from a math teacher whose name is Brian McLogan. And we're going to watch this video here together. It's going to take probably about 8 minutes or so. But he does a really good job of outlining and giving some examples on how to turn a quadratic equation into its vertex form by completing the square. So I'm going to leave you with this video for just a few minutes, and then we will come back and apply it to the example that we're looking at.
To do this. So what we're planning on doing is going from y equals ax squared plus bx plus c and converting that to y equals a times x minus h squared plus k. And there's a lot of reasons why we want to go through from standard form to vertex form. A lot of times it's easier to graph, it's very easy to find the vertex and so forth. However, it's not always so simple to convert from one to the other. So what I did is I'm going to do 3 examples for you. Now the main important thing when we look at standard form now to vertex form is we notice that vertex form has a binomial squared. And when we take a binomial and we square it, what we get is what we call a perfect square trinomial. All right, and that's what we're going to do is we are going to create what we call a perfect square trinomial. And we're going to do that by what we call the process of completing the square. So there's going to be a couple steps, and I'm just going to kind of go through each one individually. And I'm actually going to do it for each problem all together. Now, the first step, though, we need to do is we need to make sure that when we are creating a perfect square trinomial, that we have a is equal to 1. So here, you can see we have a equal to 1, so we're all set. Over here, though, I have a negative, right? That's a negative 1. So what I'm going to have to do is factor that out. Now, when I'm completing the square, I only like to factor it out of the first two terms. So I have y equals a negative 1 times x squared minus 6x plus 11. All right, now I'll talk about, again, completing my perfect square and what we're going to do. But as long as my a now is equal to 1, I'm all set. Over here, I have to factor out a 5. So I'll factor out a 5. So I have y equals 5 times x squared plus 2x plus 1. Now, again, I'm only factoring out of these first two terms because I'm going to show you what we're going to do is I'm going to now create, all right? And what we're going to do is we're going to look at only my quadratic and my linear term. So right now, those are a binomial. And what I'm going to do is I'm going to take those terms and make them into a perfect square trinomial. And I'll show you how. So to do that, what we're going to do is we're going to take b divided by 2 and then square it. So in this case, my b, if we had ax squared plus bx plus c, b is my coefficient of my linear term. So that's going to be 4 divided by 2 squared. Well, 4 divided by 2 is 2. 2 squared is equal to 4. Here, my b divided by 2 is going to be negative 6 divided by 2 squared. Well, negative 6 divided by 2 is negative 3. Negative 3 squared equals 9. Here, I'm going to take 2 divided by 2 and then square it, and that equals 1. So now what I'm going to do is that is my value that completes my perfect square. So what I'm going to do with each one of those values is I'm now going to add it to my other two terms. And what that's going to do is that's going to now create a perfect square trinomial. So let's go ahead and write that out now. So when I add that in there, so I have x squared plus 4x plus 4. Now what I have done is I have created a perfect square trinomial, and then I'll just have minus 5. Now I'll come back and I'll explain something in a second. So here I'm going to add 9 now inside the parentheses. So I'll have y equals negative x squared minus 6x plus 9 plus 9 plus 11. And then over here, I'll add 1 inside the parentheses. So I'll have y equals 5 times x squared plus 2x plus 1 plus 1. OK, so notice how everything else is staying the same. The only thing I did is I took my middle value, divided by 2, squared it, and then added it to my quadratic and my linear term to create a perfect square trinomial, right? OK. Now, adding this number is great, but you got to look at this, and we have an equation going on. When we have an equation, you just can't add numbers to one side of the equation without adding them to the other side of the equation, right? If I have an equation, if I add 1 to the left side, I have to make sure I add 1 to the right side. So that was a proper about using our properties of equality. So right now, you can see all to the right side, I'm adding a value. Now, when solving, a lot of times, what we like to do is we like to add it to the other side as well, because that's going to be your equality. However, when I'm trying to convert it from one form to the next, I'm still solving each value for y. So rather than adding the same value to both sides, what I'm going to do is I'm going to add the 4 to the right side, but then I'll just simply subtract it on that side as well. The difference being is one value I added inside the parentheses, and the other value I'm adding outside the parentheses. Well, that's very important because when I add 9 inside the parentheses, you notice that this 9 is being multiplied by negative 1. So when I subtract the 9 outside the parentheses, I have to make sure I also multiply that by a negative 1. Over here, when I add this 1, so now I'm going to subtract 1, notice that the 1 inside the parentheses is being multiplied by 5. So I need to multiply this 1 by 5 as well. All right. So why are we working with the perfect square trinomial? Why do we want this trinomial? Or what is a perfect square trinomial? A perfect square trinomial is when we have the exact same values multiplied to give us our c value, but then add up to give us our b value. So what all these perfect square trinomials can be factored into are binomial squareds. So now I just simply need to say, all right, what two numbers that are exactly the same multiply to give me 4 and then add to give me 4? And we can say that my final value is going to be y equals x plus 2 squared. And then I can just combine minus negative 5 minus 4 is a negative 9. Now I have taken this equation from standard form all the way into my vertex form. Here, when I write this, I have y equals negative. I don't really need to write the 1. So now I see what two numbers that are exactly the same multiply to give me 9 and add to give me negative 6. Well, that's going to be x minus 3 squared. Notice how I'm always getting this binomial squared. Then I look at this, I say negative 1 times negative 9 is positive 9. Positive 9 plus 11 is 20. And there you go. Now my equation is in vertex form. Over here, I say what two numbers are that are exactly the same, right? Because a perfect square trinomial always gives you a binomial squared. What two numbers that are exactly the same give me 1, multiply to give me 1, and add to give me 2? Well, that's going to be x plus 1 and x plus 1. So I say y equals 5 times x plus 1 squared. And then 5 times negative 5, or 5 times negative 1 is negative 5, plus 4 is negative 4. Or plus 1 is negative 4. So there you go, ladies and gentlemen. That is how you convert between standard form and vertex form. Thanks.
And thank you to Brian McLogan. One of the greatest things about teaching live online via Twitch on a live stream is that you can have instant guest lectures, and you don't even have to ask the person if the video is already out in public domain. So that's his take on how to complete the square, and that is our tool for translating the standard form of a quadratic function into its vertex form. So let's bring that home to this example. If I want to complete the square to discover the vertex form without needing to use technology, right? 3x squared minus 18x minus 21. How do I complete that square? Well, as Mr. McLogan did in the video, the first strategy is to factor out the leading coefficient, factor out this 3, out of the first two terms, the quadratic term and the linear term, leaving the constant term alone. It's kind of a weird way to factor. We don't usually do that, but it works really well in helping to complete the square. So if I factor out that 3, then the cofactor to it will be x squared minus 6x. Now, as he was saying, our job is to turn this quantity in parentheses into a perfect square binomial. And we know it's a perfect square binomial if the very same number that adds together to itself to give me negative 6 also multiplies by itself to give me this quantity. And that English sentence that I just said can be decoded into the following shorthand process. If I want to know what constant belongs here to complete the square, then I should take this coefficient, negative 6, and divide it in half. I get negative 3. Whoops, missed the negative sign there. Negative 3. Divide it in half to get negative 3, and then square it. That'll give me positive 9. So 3 times quantity x squared minus 6x plus 9, then minus 21. But I can't just add 9 into this expression without changing its value. So I have to offset the addition of 9 by some subtraction of an equivalent quantity on the outside. But because my 9 is multiplied by the leading coefficient 3 out in the front, and I'm adding, therefore, 27 to this whole expression when I add 9 inside these parentheses, that means I should, to offset it, subtract 27 on the outside. And now we've completed the square. The quantity in parentheses is a perfect square trinomial, and we've also done the process of offsetting the change that we had to make on the inside to make it so. Now all we have to do is simplify. And that simplification process leads us to factor this perfect square, which factors into x minus 3 times x minus 3 by design, right? We chose this 9 exactly so that it could factor this way. And then simplifying the arithmetic on the outside gives me a minus 48. So here's the vertex form for this parabola, obtained just by the algebraic process of completing the square. And again, we can read the vertex directly off of this equation because it's what's being subtracted from x inside these parentheses, and it's what's being subtracted from the whole, what's being added to the whole expression on the outside. Positive 3, negative 48. Right? That's my vertex. So that more or less covers the what we might call the abstract mathematics portion of our study for today. So what we want to do to finish up is we want to look at one example of how to bring this kind of reasoning to bear on applied problems. So how can we discover a parabola of best fit? as a companion to the lines of best fit that we discovered in the previous video when we were talking about linear equations. So finding a parabola of best fit is going to allow us to engage in a modeling process in which the underlying behavior is quadratic and not just linear. And similar to how we did it with linear equations, we're going to need some technology to actually do the regression analysis for us. How do we actually find an equation for the parabola of best fit for a set of data? So we're going to start with this data set. This is a data set that I'm borrowing from a website called LearnZillion.com. And it's data that originally came from the CDC, Centers for Disease Control, which reports a relationship between the number of years since the year 2000, that's the X variable here, and the number of cases of AIDS, the HIV virus AIDS, reported in the US in that given year. Right? And so our data starts from X equals 4, so that's the year 2004. It goes out to the year 2013. And the values of Y here, the number of US cases of AIDS, is measured in thousands. So I probably should have mentioned that. So I'll say thousands of US AIDS cases. That's what the Y variable here is measuring. And so when we scatter plot this data, it looks an awful lot like there is an up and down trend in this data, right? It begins increasing from 2004 right up until about 2011, and then after that, the trend turns around and begins to decrease. And so if we have a quadratic model for this, if this data is well modeled by a quadratic function, we can ask our two salient questions. We can ask for those two salient features. On the one hand, we could ask about the intercepts, and the intercepts tell me where the value of Y is equal to 0. Well, what's going to happen when Y is equal to 0? It means that the number of AIDS cases is going to have fallen to 0. So that's one important question that we can ask. Ask for the x-intercept of my quadratic model. Right? That'll tell me when the number of AIDS cases has decreased to 0. On the other hand, we can also ask, what does this model predict were the maximum number of AIDS cases? We can kind of see from this data that the graph goes up and then it goes down, so there was a maximum in there somewhere. And we can directly read from the data that it looks like the maximum happened somewhere around 2011, give or take a little bit, maybe somewhere near 2010, maybe somewhere near 2012, but it's in there somewhere. But we could use that quadratic model by asking for the vertex. And if I find the vertex, then I will have an understanding of where the maximum value of this quadratic occurred. But in order to do either of those things with algebra, we need to have the algebraic model. We need the formula in order to do that. So how do we get a formula that will help us to model this quadratic relationship? We're going to look at it first using Desmos, as we have in the past. Sorry, let me get my browser here set up appropriately. So the first thing I want to do is I want to type into my Desmos window. I just want to type the prototype equation that I want to try to use for this model. And so since I want to use a quadratic function to do this modeling, I actually can choose in Desmos whether I want to have standard form or whether I have vertex form. Basically, Desmos is just going to follow my lead. If I want a standard form equation, I'll just write y equals ax squared plus bx plus c. This is probably the way that we'll want to do it most of the time. I don't necessarily trust other ways of doing it just from a computational perspective. And so to get Desmos to actually do the regression, we'll turn this equal sign into a twiddle, right, the little thing on the northwest corner of your keyboard, and turn all of my y's into y1s to tell it to use this set of data right here in the y1 column here, right, and then turn all of my x's into x1s. And once I'm done with all of that, now Desmos helpfully gives me a parabola. And it also performed the statistics to give me some values for the parameters for this parabola. So here I have an equation. I'm going to write it down on a separate screen here. You won't be able to see this. But plucking out these coefficient values for a, b, and c, we find that the function model, f of x, is equal to negative 0.69. I'm just going to round to 2 decimal places. X squared plus 15.009, so I'll round that to just 15.00 times x, minus 40.12. 0.12. Great. And so based on the output that we got out of this regression, we now have an equation for a parabola which actually looks like it pretty closely passes through all of these data points. And we can say that it's pretty close because take a look at this r squared, that's my correlation coefficient. Take a look at this value, 0.9994. That is awfully close to the perfect correlation value of 1. Right? So similarly to our linear regression examples, the closer that this correlation coefficient is to 1, the stronger the model, the closer that the equation that we discover matches the data points that inspired the equation in the first place. So this is a really good model for the behavior that we're seeing here. So let's take this opportunity to do some algebra with that model. So if I wanted to answer the two questions that we posed, which is first of all, when the number of AIDS cases falls to 0, and the other question was when were the number of cases at their maximum. Oops, having some trouble with my pencil here. When were the number of cases at a max? Right? Remember that these two questions are really asking us to find the x-intercepts of my parabola, respectively, and the vertex of my parabola. All right, so let's go through the algebra of doing this process. For the x-intercepts, I particularly am not keen on trying to factor this particular quadratic. Most quadratics do not have a nice factorization with nice whole numbers in them. So I'm going to take the computational way out, and I'm going to use the quadratic formula. So for my quadratic formula, minus b plus or minus the square root of b squared minus 4ac, and then all that gets divided by 2a. I'll go ahead and evaluate that expression for a equal to minus 0.69, for b equal to 15, and for c equal to negative 40.12. And when I place those values into here, minus b becomes minus 15, b squared becomes 15 squared, 4ac becomes 4 times negative 0.69 times negative 40.12. Make sure to extend my radical sign, extend my fraction bar, then the a in the denominator becomes negative 0.69 as well. Okay, so there is my quadratic formula evaluation. Now I'll do this piece by piece, right? 15 squared is going to be 15 times 15, 225. I can do that one in my head, but the next one I don't want to do in my head. 4 times negative 0.69 times negative 40.12. For that, I'm going to pull out a trusty calculator. 4 times negative 0.69 times, 4 times negative 0.69 times 40.12. And this negative and that negative are going to make a positive, positive 110.73. And then there's a minus in front of that, so we end up with 225 minus 110.73. Do that arithmetic out, and underneath the radical, I get 114.27. All right. And now is a good time to quickly pause and make the observation that we made earlier today, which is that this number underneath the radical, the discriminant, tells me how many x-intercepts my parabola is going to have. Since it's positive, that means that we have 2 x-intercepts for my parabola, which is something that we noticed from the Desmos graph already. So that shouldn't be a surprise, but it's reassuring to see at this point in the process, right? Because after all, just to give you the quick view again, there was our parabola, and it has 2 x-intercepts. One's right there, one's right there. Okay. So coming back to this, in the denominator, we'll finish that evaluation. 2 times negative 0.69. That's negative 1.38. If I take the square root of 114.27, I get 10.69. And I'm going to add and subtract that to negative 15, and then divide the results by negative 1.38. I do out all of that gory arithmetic, and I end up with two answers. On the one hand, when I take the minus sign, I get 3.13, and when I take the plus sign, I get 18.53. And those are then the two x-intercepts for my parabola. Coming back to the graph itself, there they are, right? X equals 3.13 and x equals 18.53 on the other side. So the question, if we go back to the original statement of the question that I asked here, is what does this model predict will be when the number of AIDS cases will decrease to 0? And so that decrease to 0 mindset sort of calls to mind, oh, we're talking about something that's happening in the future, something that happens after my data set. My data set ended in the year 2013. So probably the point that the question is asking for is the second of these two x-intercepts. It's the 18.53, not the 3.13. And so we would answer this question, when does the number of AIDS cases decrease to 0, by saying something like, when x is 18.53, i.e. in the year 2018, right? So that's how we would then answer that question based on the information that we got out of this x-intercept. And we got that x-intercept by using the quadratic formula to solve our equation. Okay, so that answers the question, when do we think the AIDS cases are going to fall to 0 in the year 2018? When was the number of cases at its maximum? For the vertex, again, we could go through the process of completing the square if we want to, but I'm going to take the approach that you're probably going to take as well when you do these problems, which is to take the quick and dirty way out, find the x-coordinate using the quadratic formula. In particular, just using that first piece of the quadratic formula, minus b over 2a. Minus b is going to be minus 15 in the numerator. 2a is 2 times minus 0.69. Minus 0.69. And when I divide those two things, 2 times minus 0.69 is again minus 1.38. I divide minus 15 by minus 1.38, and I get 10.89. So, armed with that 10.89, let's go back to the graph one more time. 10.89 is an x value, right? It's going to be somewhere here between 10 and 11. And it's this point up here at the top. There's my vertex, right? 10.89. There's a little bit of round-off error in our calculation, so these 3 decimal points in Desmos are not quite what we have. But ours is accurate to how we've rounded off the coefficients. So there's kind of a lesson not to round off too early. Try to wait until the end to round off if you can. But so there's the vertex. That's the x value. And of course, if I want the f of x value, it's going to tell me how many AIDS cases there were that year. I would just plug this number, 10.89, back into my original formula for my function. And when I churn that out, 10.89 is going to give me about 41.1, right? And so the year in which we get the largest number of AIDS cases according to this model would be when x is 10.89, i.e. in the year 2010, and the number of cases that year was 41.1. That was the y value. And since the y value is measured in number of thousands of cases here, 41.1 thousand cases. Or if you like, 41,100. Right. So there's how we can then get information into and out of this quadratic model once we have used a quadratic regression to discover this model in the first place. So that's how to do quadratic regression modeling using Desmos. But just for the sake of completeness, I think it might be a good idea for us to see also how to do this same process using a spreadsheet. Because if you're not using Desmos out on the job, or if you're not using it in your other business classes or something like that, how can we do this process using either Microsoft Excel or a Google Sheet or some other similar sort of spreadsheet technology? How do they handle quadratic regressions? So let's make that our last topic for today. So I'm going to open a Google Sheet right here and quickly enter in the data. Let's see, how do I find that data again? Just rip out this tab, type it in here. So the x values ran from 4 up to 13, and then I'll type in the y values by hand. They're 8.804, 17.512, 25.102, 30.744, 35.661, 38. This is super exciting television right now. Me typing a bunch of data into a spreadsheet that you can't even see right now. 37.832. Okay, great. So I've loaded all of my data into a blank spreadsheet. And now let me give you a look at that spreadsheet. All right, we're going to switch over there. Cool. All right, so there's all of my data loaded into a Google spreadsheet. Right here, all my X's, all my Y's. Remember, X is the number of years since 2000. Y is the number of AIDS cases in thousands in the US. Okay, so to finish, how we would do a quadratic regression using a spreadsheet is usually spreadsheets for any other kind of regression besides linear require you first to create a chart. So I'm going to just choose to insert a chart based on this data, and the chart type that I want, all of these, every single one of these times is a scatter chart. Okay. So here is my scatter chart, and it's not a very elegant one. This happens in every spreadsheet. The first chart that it shows you is not particularly illuminating. I'm going to try and expand this here, make it a little larger. But to get a regression, usually the way that you'll do it is by, let's see, is it going to let me do this here? Is by adding a trend line. So in Excel, you can add a trend line just by right-clicking on one of the data points and choosing to add a trend line. In Google Sheets, it looks like what we need to do is actually click the chart editor under Customize. At the very bottom, let me actually take a moment and make this bigger so you make sure you can see it. Down at the bottom of the list here is the option that says trend line. So if I check trend line, now the first thing that Google does, and Excel does this too, is it just puts a linear trend on the graph. We don't want a linear trend. In our case, we want a quadratic trend. And a quadratic trend is a polynomial whose degree is 2. Right? So that's another name for quadratic. Right? And now that we've changed it to polynomial of degree 2, now it looks an awful lot like the graph that Desmos provided for us. Right? But what we don't have yet is we don't have the equation. And so we need to have our spreadsheet actually tell us what the equation is. Use equation. And then also show R squared value. And that will show us what the correlation coefficient is. And so if we, it's really small and hard to read, so let's zoom way in on that for a minute. This label that we see up here at the top of the sheet, there is my equation. Negative 40.1 plus 15x plus minus 0.693x squared. That was the same as the quadratic equation that Desmos came up with. And it also is reporting the R squared value right here, 0.999. So you can do this with a spreadsheet. You can do this with Desmos. I happen to use Desmos because it's a little bit easier for demonstration purposes. But when you're doing more high-powered kind of analysis for your other courses or out on the job, probably a spreadsheet is what you're going to end up using. So that closes the book for today on quadratic functions and quadratic modeling. Our next steps as we move forward are going to be to amp that up still further and study polynomials of higher degree. A lot of the intuitions that we built today, and particularly the factored form, is going to be our key tool for understanding how polynomials of higher degrees work as well. So those are going to be our next steps, and I look forward to doing it with you starting in our live streams next week.